All right, so we are looking at, so here's like an example of a simple expression, right? So z equals x plus y. So first thing, when we're solving any problem, we have to understand the problem. So we started off with some things that are simple expressions. Now remember, in the assignment, I said you should support expressions of all forms from 4.2. So that includes crazy stuff. We have parentheses somewhere, right? Yeah, like down here. So including things that have parentheses. So we should support addition, multiplication. Is there subtraction somewhere? Yeah. Subtraction.
There was some tiny division.
Anything else?
By the way, how we support subtraction?
Do we get an example of subtraction? No. Well, then we're going to have to add the 2's complement. That's what we'll have to do. Subtraction's done through addition using 2's complement.
No, it's not in the mips.
What do you mean it's not in the mips?
Mips is not doing it. It has add or sub. Adder or sub chips doing that.
Okay. Well, here, what do we do? Oh, so yeah, so you'll just do the same thing except you output it a sub instead.
Yeah.
All right. So, but just as a simple thing here, z equals x plus y. Remember, when we go from the C to the MIPS, we don't necessarily care about variable names. All right, so they're loading into T3 value. So they're basically creating two variables, one for x and one for y, giving you a home base for these variables. So just like our last time, we had to grab two unused registers. All right, and then we're going to add T3 plus T4, storing the result inside of T5. So T5 is kind of our Z, right? And then we will write to, we're going to store. So we loaded some stuff into there. Now we're going to store at T2, which is our output, right? Our T5. So that'll give us our final solution. So this is for a simple expression. But now when we have more complex expressions, like the one down here, this one, they say break it down into smaller pieces. So we can say that z is equal to x plus x. Then we can say that z is equal to z plus y. Then we can say that z is equal to z plus 1. So you break it down. So you're always solving the problem of some variable is equal to two other things with an operator in between them. Mm-hmm. That's the problem we're always solving.
I remember what the conversation was about.
Which one?
The Facebook comments.
Okay.
I remember you were asking me what I was doing, and I said I was looking up the Bible, the verse we were talking about. Remember we were.
Oh yeah.
One chapter that was like.
Yeah.
On something really bad. And you said you're doing that right now, and I said, would you rather?
Yeah, right.
Boom. Okay, continue.
Thank you. All right, so we have a complex expression like this. We break it down into its smaller pieces where we always handle a single value, operator, another value throughout. All right, so we're breaking this down into its small pieces. So we're always outputting, because remember in the assignment, I think I said you did not have to use efficient assembly, right? Making it more efficient would have been problematic. That would have been more difficult. But I gave you the easy version of the assignment that just says, look, as soon as you solve the problem for the simple case, solving the problem for the simple case where I have some variable is equal to another variable, operator, another variable. You know, what this operator is depends on what we spit out here, right? So add, subtract. Is there a divide in MIPS?
No divide.
Okay.
Only add,
subtract, and multiply. Okay. So what this operator is dictates what this line is. Correct? Everything else stays the same. All right.
I think it also depends. For instance, if you having say x plus 1 using adding, but x plus
Oh,
5
for add I,
using
if one of your things here is an immediate rather than a variable.
Another
Yeah.
thing is if using multiply, say x plus x times y, technically it's you have to load two variable, but if it is x times 3, so you have to load 3 into your register first, then using multiply.
Well, right. So we have to know the nature of our two operands.
You know if it's a number.
So we're going to look at the operator. That operator is going to tell us the kind of math we're going to do. And then the nature of those operands is going to tell us which specific function we're going to call. Is it add or is it add I?
Mm-hmm.
Right? Something like that. Okay. So let's go ahead. Let's see. What do we want to do first? We want to implement the simple version of this first and then do shunting yard second. Because simple version first is going to give us kind of our cookie cutter for taking anything that's in that form and spitting out equivalent assembly code. Mm-hmm. All right, that makes sense. Let's see. Loaded into registers. So are they saying that T0 and T1 are always our two parameters?
I don't think so. Say if you having more, it should be, because in the later chapter it's saying that T0 is the first parameter, T2 is the second.
But we wrote this, so we can write this in terms of what we wrote last time.
The new one.
So last time we have here's our mips.
Are you looking at it correctly?
I think so. Is it a mips compiler?
Oh, that is right.
Mm-hmm.
So our mips compiler took in our test. Our test looks like this.
Oh, it will open Xcode, I guess. Oh, thank goodness. No.
All right. So it looks like this. Where we define a variable, we give it a value. So we want to be able to get the registers that those values are in. We already have the ability to do that. So if we follow this from last time, just to recap. So we have our MIPS compiler. What is our MIPS compiler? It's this guy. MIPS compiler takes in the file name. It reads the stuff in. As long as you have still instructions to process, we read in the instruction. If it's end of file, we say break. Otherwise, we process the instruction. So up to this point, we only have instructions of two forms, right? We have a form that is starting with an int. This is the defining a variable version. Or we have a simple expression instead of an arithmetic expression. Okay? So whenever we run into a simple expression, so the idea here is we might say int I is equal to, int I, then I equals 7, j equals 14, I equals 2, and then we might say that y, actually we would probably do something like int y, and then say y is equal to I plus j, something like that. All right, where I and j already have registers associated with them. Right? So I and j are associated with T1 and T3 or something like that because our compiler did that. All right? So this would be creating new variables like we had before. And then we're going to set y equal to a value. What value? At this point, we're going to do our arithmetic expression where we're going to resolve the register this guy was in, resolve the register this guy was in, presuming they were both variables. If they're a number, if they're a literal type, then we would not have to look up the variable name. It wouldn't be associated with the register. Instead, we would grab a new register and load that value into it.
But I have a question.
Mm-hmm.
I think in the CPU, saying I equals to 7 when you assign the I, technically
you don't even need a register.
They kill the register. They make it as unused, I think.
After the fact?
Yeah, they should.
Yeah, we could actually do it without the register.
I think it only remember the memory address.
Mm-hmm.
They know I is in which memory. Then
So one of my biggest problems was trying to understand how this is gonna even remember which register is taking.
Well, and that's why we're going back through here and reminding ourselves how this works. So if we're looking at an int, so this goes back to what we did for last week. If we have this, we're going to go ahead and we're going to get ourselves a register for storing that I. So if I'm looking at an int here, what am I going to do? I'm going to be adding an immediate because we only support something is equal to an immediate value. That's going to be my output. All right. And I'm going to go ahead and get my variable name. So this extracts the variable name from the semicolon thing, everything after the equal sign. All right. Then I'm going to ask my register collection to get me an available register.
Yeah.
So something that's not currently being used. All right. And then I'm just adding stuff to my string. And then ultimately I'm going to say the data memory, get address from memory. So this is going to give me a place to store things. So if I roll back here, we go into here. We go to our assignment operators. This is what we solved for last week. So just defining a variable does this. It says find a unique register, an unused register, add 0 plus some unique memory address, right? So load a memory address into that. Then we're going to add I. So these two lines are related to this next line here, the x equals 7. So we're going to say T1, so that's a new unique register we're going to use for doing some math, is equal to 0 plus the 7. And then we're going to store. Now, store puts things where? In registers or
memory.
Data memory. Okay, so storing something puts, we're going to store the value of T0, this guy, well, at the location of T0, rather, the value that's currently in T1, which is the sum of 0 and 7 in this example. So this guy right here puts a 7 at memory location T0. So now we have that value actually stored somewhere in real memory.
Yes.
That makes sense? Okay. So we go back to this. So here's our pieces here for this guy. So we're going to do an add I. We're adding I 0 onto some place in memory. This is when we define that variable. All right, now that variable does not have a value yet. Can we do math with a variable that doesn't have a value, or would that be an error?
I think if the register doesn't have value, it's in 0. It's just.
That's assuming a default value, but so realistically, it doesn't make sense, right?
But we can assume it shouldn't be used.
Right.
We have to,
If I've said int x, and then I say y is equal to x plus 3,
it probably will
that's
be wrong.
yeah, that should not work.
Okay, because that's what I did.
All right, because x doesn't have a value in it.
No, yeah.
All right. Now, we could say that the default value is 0, so we'll actually stumble upon how default values are handled here as we do this. But generally speaking, when you define a variable, we are expected to give that variable a value. So that's why we're doing it on two separate lines here.
Yeah.
You know, most modern languages, we would say int I is equal to 7 and do it all at once, and that kind of has double meaning. But for ours, we're doing this simplified. So this is defining a variable, defining a storage location, and this is putting a value in that storage location. We would say it's not allowed to do math with that variable until it has a value. Fair enough? Okay. All right. So going back through this if says, what do we do when we, so I'm going to put some comments in here. This is define a variable and associate it with memory. That's what that does.
Can you just using declare?
Huh?
Declare?
Well, whatever. Define, declare, doesn't matter?
Doesn't matter, but it's a terminology.
Here, I'll put a couple of extra n's on there for you.
Okay, that's it.
All right, so we're going to define a variable and associate it with memory. Otherwise, what are we doing? We are assigning a value to a variable and storing the value in memory, not a register. In let's call it data memory. That's what we call it in MIPS, right?
Yeah.
In data memory. All right, so we're doing our splitting stuff, blah, blah, blah. We're going to get some more register collection stuff to give ourselves my thing to do my math. Then we are figuring out our var value. So we're looking at a line that maybe looks like this. So we have I is equal to 7. Presumably, we already have this variable I associated with a memory address somewhere, right? All right, so we're going to output add I. So anything with the output is what the code we're putting out is. So if we go back into here, x equals 7, what are we doing? We're going to load this 7 into an unused register. All right, that's the value. Now, I think something he was saying before is at the end, when we're done with that register, we want to be able to release it. Saying, look, I don't need this register anymore. It was only a temporary thing. Now I don't need it. So we'll address that here in a second. All right, so we're going to add I. We're going to get ourselves the name of an unused register. That's this temp_reg name. Then we'll output that temp_reg name. Then we'll do the whole 0 thing. And then we're going to get the value associated with that. And this guy assumes it's a literal value, a number, 6, 7, 8, 2, whatever. Okay? So that's what this code up to here does. All right? This does this piece, this first line. Add I, unused register, 0 plus the value we're loading into it. All right, I need to temporarily hold that literal. Now, my next line, this is where I actually put something into real data memory. Okay? So that's happening here. So I'm going to output SW, so I'm storing a word. All right, store means put into memory, as opposed to load means bring it into register. So store means put into memory. Where am I going to put it into memory? Well, what? The first thing is, what am I putting into memory? That is whatever's currently in temp_reg name. That's the what am I putting into memory. All right, then our output, this is our offset, right? So 0 offset based off of, this is where we get our old register name. So we're going to ask our register collection to get us a register name given a variable name. So this is the guy I can pass and say, give me the address of I. Make sense?
Yes.
All right. So this is going to give me a register collection, get register name by var name. So that's going to give me a register, and now I'm giving it the old register name. Now at this point, we're working with registers, but has the SW, so we got to take it one step further. We have written assembly code for storing a word. But the assumption would be that after we've executed this line of code, so we've done this line, and now we just did this line. If you think about the result of code post executing this second line here, what do we have? We have some place in memory being equal to 7.
Yep.
That make sense?
Mm-hmm.
I need to remember
Yep.
that place in memory. That's my variable environment. That's going to become pretty important later on when I start using those variables.
Yeah, and even when you're doing like y equals to I plus j, you don't really have to store that in memory to calculate.
Mhm.
You just work with load, right? You're not gonna store them because you can like really just do all the add-i's, then the load, and work with the registers only before throw that in memory.
Well, right, but we think about, because in the assignment I mentioned that you don't have to worry about running out of registers. But we can imagine that if we just keep using registers at our whim, that we would eventually run out of registers probably fairly quickly,
Very quick.
right? We don't have a whole lot of registers to work with here. So at some point, that's why we're throwing it into RAM. So once I've defined a variable here and I've given it a value, my ultimate goal is I want to put that value into memory somewhere, and somewhere I want to remember. I want to map and say the value of a variable named I is stored in memory at bucket whatever in memory. And his value is 7. That way, once I've created that relationship, I can relinquish all of my registers.
You can release it.
Right? So I have a couple of mechanisms here that I need to do. I need to be able to give back my registers, because one thing we can't do with what we did last week is I can't say int I equals 7, and then int j is equal to I. I can't do that right now.
You probably can.
Because since I'm not releasing the registers, I do still have it in a register. I can't do this the right way right now.
But you can use it in a hacking way.
Yeah, right now, since I do collect everything in registers and I never give them back, I can ask for the register that I does live in and get its value. But presumably, we can't rely on the value of I living in a register long term. Mm-hmm. The idea is we resolve a variable, and its value is where it's stored in actual memory. This is like a pointer in a typical programming language. All right, so let's add this additional ability here. All right, so at this point, we have a register name that has our value. Now we also have a temp reg name. So if we go back into here, so this was our temp register. So temp reg holds the value, and our register for the variable we're trying to hold, it holds the memory address. The result of an SW says we are actually going to put a value in the memory address. What I need to do is I need to actually make memory match that. Mm-hmm. Or at the very least, I need to have my own mapping. Mm-hmm. Okay, where I say that variable X is associated with memory address 5000.
Yeah.
I need to be able to go and ask that question later. Get address given var name. Something like that. All right.
In the later chapter, they split the memory into different zones.
Mm-hmm.
Like those one probably will be either in stack memory, based in a function, or it's like a global memory somewhere.
That could be worked with. That could work with an array, for example. That you create an array and.
Array is.
Just a temporary.
Array is not really in this concept.
What do you mean? Like
create an array receiving all the values, then you can look up later.
Well, yeah, we could fake data memory with an array if we wanted to, but I don't think we need to do that. So if we look at data memory here, data memory is here's your array. We have an array of mem buckets, right? So this is how we're representing our RAM. All right, and remember, what is a mem bucket? A mem bucket is a location and a value and whether or not it's currently in use. So we'd like to set this guy at bucket, for our little example here, at location 5000, we want to put a 7. And we want to mark that guy as being in use.
Yes, okay.
But we need one additional thing. We need to know that there's a variable associated with it. Right? I need to know that X is the value associated with this particular guy.
Yes.
All right. So what we can do here is for our mem buckets.
Didn't we do variable name, var name?
We did it for registers last time, didn't we?
Oh, okay.
Yeah. So for register, we let a register know what var name was associated with it to give us a convenient way.
So technically it is wrong.
Yeah. It's not wrong. It's right for what we wrote last time.
Yeah, but it's wrong in the bigger concept.
Yeah. I mean, it gives us what we needed. It allows us to remember that we put a variable associated with this into this register for the most recent moment.
Temporarily.
Yeah. Whereas that moment is going to be passed pretty quick, because as soon as we're done actually storing the value of a variable into memory, that register should be cleaned up now and available for somebody else. So we have to have two different mechanics here. One mechanic is going to be when I'm done using a register, release it. All right, so we can write that one. Well, let's do the data memory thing first since we're currently staring at this.
one is not matter.
All right, so data memory uses a whole bunch of mem buckets, and we're going to go ahead and say that a mem bucket also is associated with a var name. Okay, and we're going to have, we could do, how did we do it for registers? Did we set it after the fact, or we do it as part of the constructor?
You put in the after.
We have a set var name. Yeah, set var name.
Yeah.
Okay.
I think it makes sense because you want to use a memory. It
Sure.
doesn't really have to link to.
Yeah. So in our constructor here, we'll go ahead and say this dot var name is equal to the empty string. So by default, a memory bucket is not associated with a variable name. But then we're going to go ahead and I'll do my source generate getters and setters, and we're going to do a getter and a setter for var name. So we have a get var name and we have a set var name. So now we can externally let a mem bucket know that he's actually related to a variable name for the time being. Later on, we have, if we think about Java, we have automatic garbage collection. So at some point in time, we go back through and we unassociate mem buckets with, variable names or being used by a program or something at all times, let's say.
But actually, saying in C, you technically program should
Delete it themselves.
on
Yeah.
their own.
Well, yeah, but in Java, somebody's going to release memory.
Yeah.
So whether it's you as a C programmer releasing the memory or it's Java releasing the memory, doesn't matter. Somebody's going to release the memory. And what does it mean to release the memory? It means mark it as not being used and unassociate it with variable names. That's what releasing memory ultimately will mean. Okay. In fact, we can even give ourselves a little function here. Public void release for this mem bucket. And what does release mean? Maybe we reset it.
Reset.
So we set the in use to false.
Yeah.
So we'll set the value to 0. We'll set in use to false. And we'll set var name equal to. Now, one thing we could do if we didn't want to have a duplication of code here, we can say private void init bucket like this. Put these three things in here. And then what we can do here is set the location, but then call this dot init bucket, and then in release, it's this dot init bucket. All right, so now data memory knows how to initialize itself and release itself using the shared code. So when you have a brand new brand new mem bucket, it's going to start off with a value of 0. It's going in use is going to be false. It has no variable name associated with it.
Wait, I'm confused. Why did you do that? I mean,
Because I'm calling it here and I'm calling it here. So rather than having this code duplicated in this place as well as this place, I wrote it once and called it from both of these places. What that does is it allows me to say, oh, well, I actually want init to do this dot location is equal to -1. I want it to do a little bit more than it used to do. Now I can just change it here rather than having to change it in 2 different places in code.
Okay, but why? I mean, like, init bucket and release does the same thing essentially. But I guess what you're saying is, if we wanted to make some changes to init bucket, we wouldn't have to make changes in release.
Well, correct. I mean, I have 2 places. This one function here is currently being called by 2 separate places. I'm calling it from my constructor, and I'm also calling it from release.
Right.
right? This exact same code.
Right.
Now, a few minutes ago, I had these 3 lines inside of membucket. I had it here. And down here, I had those same 3 lines here. So one of the goals in object-oriented programming is you don't want to duplicate lines of code. Now, would this have been the end of the world? No. I mean, this is 3 lines of code. If I changed one line, it's not the end of the world. You can just go up here and change. If I wanted to add one more thing to initializing a membucket, I can just change it here and then also change it here. This would just be better programming practice. And I made this guy private, so he's only accessible inside this class. So I'm just having my constructor as well as this function that we haven't even called yet in the wild, but this release function. Go ahead and say, this is what it means for a membucket to either be born or to be released. You know, both of these guys effectively do the same mechanics.
Yeah.
Make sense? So this wasn't necessarily a necessity, but I think it's probably at least reasonable programming practice. And now we have the ability to give up a membucket later on if that makes sense to us. And we're going to do it because we're going to also have to do it for registers. Okay, so for a membucket, we now know how to store var names, and we've given ourselves getters and setters for var names, very similar to what we did last week with registers. All right, because this is going to be helpful for us for our data memory, for us to go through data memory and say, hey, I need the memory address of variable X. Make sense? So now I'm going to teach data memory.
You
Now-
can also giving, say, find the memory by variable name.
Yeah, that's what we're putting in here.
Oh, this is not in that file.
In data memory?
Oh, I say, I thought like you're going to put in the memo bar.
No. I'm in data memory.
Okay.
Yeah, data memory is going to have a function that says, because data memory's job is to hold on to an array of membuckets. So we have all of our memory represented as a giant collection of membuckets, and we're going to say, I want you to look through those membuckets and find me the membucket that has a variable with a name and what memory address is associated with it. Now, one weakness we're going to have in here is that since we're not dealing with variable scope, and you kind of said you know when you look ahead at the memory stuff on the chapter, you do want to have kind of local memory for an individual program, because if we just think of data memory as a giant big bucket of memory for your entire computer, is it possible that we might have 2 different programs running our computer at the same time that both have a variable named X in it?
It's very likely.
That's probably likely, right? Or at least a variable name I, as often as we use for loops to say for int I. So we're not really covering that in this. You know, we could have data memory that's associated with an individual program, but for our world here, we're okay because we're actually only looking at the compiled code for a single program, which is fine. How it actually gets implemented under the hood is less of an issue, let's say. All right, but for data memory, when we get an address for new memory, we also need to be able to set a variable name for an address. So we're going to say public void set var name given address. Now addresses by our membucket come in the form of a int. So this guy will take in an int location as a parameter, and what we're going to do is we are going to spin through our array of buckets, and then what did we give ourselves a so our buckets are a multiple of 4, so we have a byte size. All right, so we have a whole bunch of empty membuckets in here, so we're going to go through and find the membucket associated with a particular location. All right. Now, because this guy is technically in contiguous memory, we could actually do the math to get us right to that bucket, because the address should be a divisible by 4. So the starting point is 5,000, but I stored that inside. We could make it faster, but I'm just going to go through and search it real quick, just to keep this part simple. This isn't, a life-changing event type thing. So I'm going to say for int I is equal to 0.
Why not just copy the code?
Huh?
For in.
Oh, because I used the for
Yeah,
that's fine.
it's the same. Technically.
I did a for each loop for that guy. Actually, you know what? Let's just do it without a for each loop so we have both examples. For int I equals 0, I is less than this dot the buckets dot length I plus plus. So instead of using a for each loop like I did here, I'm going to be looking at if this dot the buckets at bucket I, which is a mem bucket, if that guy is in use. Okay, so first of all, if he's in use, and this dot the bucket dot buckets at bucket I dot get var name dot equals. I'm going to kick this down the line here. Actually, I'm not looking for var name. I'm looking for location. Dot get location is equal to location. Then I want to go ahead and say this dot the buckets at bucket I dot set var name equal to, this guy needs to take a second parameter of var name. I'll set it to var name. For our code here, we can go ahead and assume location does exist, that they're giving us a real memory address. So set var name given address, we're going to say here's the address. I want to associate that variable name with that address. So what am I going to do? I'm going to go through all of my mem buckets. I'm going to ask if this mem bucket, actually at this point I don't even care if it's in use or not. So I don't even need to really ask that question.
I don't think
It would be a syntax error, you might say, if you try to associate a variable name with a memory address that's not in use. But since we're not error checking anyways, we could just say, if the bucket I'm currently looking at has the location that you told me about, I'm trusting you on this, then I'll go ahead and set that guy's variable name equal to the var name you gave me. All right, so this will set the var name given an address. Do we have a value somewhere? We need to have a value for this too. Public void set value given address, and this is going to take a location. It's possible we could have done those all in one move, but I'm thinking there might be points where we want to have granular control over whether we want to just set a variable name or whether we want to set a value. We might not want to necessarily do both of those things at the same time.
I think it's not in the same time because we have declaration and we have assignment.
Well, at the very least, worst that happens is we call it twice instead of being forced into having one function that is too much. So this will go through all the things. If we're looking at the right location, then we want to take in the value, and we're going to go ahead and set the value equal to whatever value was passed in. All right, so this guy sets the value given an address, looks through our mem buckets, finds the address we're looking for, and sets the value there for that guy. All right, now we want to be able to get the value given a variable name, right? So public int get value given var name. And this guy's going to take in a string var name. And we'll do this one as a for each loop. So we'll say for mem, how do you spell mem bucket? Mem bucket. That. For mem bucket MB in this dot the buckets, let's do something. We're going to ask the question. Again, we don't actually need to ask if it's in use or not.
Yeah.
We're assuming it's accurate, so we can say if mb dot get varname dot equals varname, the guy that was passed in. If that's true, then we're going to say mb or return mb dot get value.
Then you're going to throw exception.
Why do they do that every week?
Well, chase him down the hall. Oh, he's going to go beat him up. It's going to be awesome. Hey!
They went off running.
Did they? They saw you?
Yeah, I'm gonna get them next time. I'm gonna bring my gloves in next time.
Yeah. All right, so this is what we'll do if we actually find the guy we're looking for with the var name. Right now, this guy's yelling at us that we need to return a value, so we'll just do a throw new runtime exception, but can't find var name. KK, thanks.
I have a question for Java. So why I cannot directly throw
Need a
new
who?
exception, but I can throw new runtime exception?
Here.
So Mike, why we cannot throw new exception, but we can throw new runtime exception?
You can throw a new exception.
If you try to say throw new exception, actually you have to.
You have to say this guy throws an exception.
Yeah, I just was wondering.
Yeah,
why-
runtime exceptions don't make us advertise that this guy will potentially throw an error. If we advertise this guy might have an error, then whoever calls him has to deal with that error. A runtime exception is like our get out of jail free card. It's saying, look, this guy could cause a problem. I'm not going to deal with it, and I don't expect you to deal with it. So I'm going to give you a runtime error. You're going to get the nice red text that says something bad happened.
Just break it.
Okay, and you could catch it. You could choose to try to do something and catch that exception. I'm just not forcing you to catch it by advertising that this guy throws an exception. That make sense?
So it's just like a Java syntax.
Yeah. So by saying this guy throws an exception, what that says is whoever calls this must deal with that exception. If I omit that, now I'm saying this guy doesn't necessarily throw an exception. He might complain a little, but you don't have to deal with it if you don't want to. All right. So this is like our, I don't know.
Then for convention, should we actually trying to throw a exception anywhere we think it might throw exception? This might get in trouble? Or like what is the common practice?
Common practice would be this. If you have a function like this that is advertising that it will return a value, and you have to deal with that, where you're in a situation like this where I might say, I know that you gave me a variable name, I know I will find it in here. Okay, we're making the assumption that whoever's calling this function is going to give us good information. It's going to give us a variable that we've stored somewhere. All right, but Java still says we have to return a value.
Yeah.
If for one reason, so if I leave that out, I can say that I know for a fact, I might not know for a fact, but I can pretend like I know for a fact that I will find var name inside that loop. Java doesn't know that. So Java's not happy that I have not returned a value in a guaranteed way. I only conditionally return a value in this if statement inside of this for loop. So in order to make Java happy, I need to say, look, if I'm still alive here, something bad has occurred. I'm going to throw a runtime exception, which now makes Java okay with me not returning the value. So I would say that that is acceptable use for a runtime exception.
Okay.
Because it's going to be common for you to write code that will either definitely return the value in here or
It's indeed impossible.
that may or may not be recoverable. If I'm still out here, I might choose to recover from it and do something else, and maybe I still return an int. But at this point, if I went through my entire for loop and I never got to a value that I can return,
That's maybe
You know,
something wrong.
at this point, I'm out of options. Like you asked me for a variable name, I checked all of my RAM, didn't find it. You want me to give you an int, I don't have an int to give you. So I'm just going to throw my arms up and say runtime exception. That's my option. Make sense? All right, so that's our, would be acceptable use. Now, if you have code that legitimately could cause a problem, I saw her, yeah.
Okay.
You have code that legitimately could cause a problem, and you want to force whoever called it to deal with it, then you would say, I'm going to throw an exception from this so that now you're forcing your code to be policed. At that point, you're saying whoever calls this, they have to deal with me complaining. In this case, they could optionally deal with me complaining. Yeah.
So I just want to make sure I'm following this right. So the value you're getting is whatever value is being set to each variable, right? Because you're not really throwing the variable inside the memory, you're just throwing the value.
Correct. Yeah. By our example here, what was it? This? Yeah. If I associated 7 with I, what I'm getting here is if I passed in an I, I'm going to get the 7.
Okay.
That's what that's going to give me, is the
Alright.
value associated with I.
So the variable itself can never go inside the memory. In those cases, it will just.
Correct. We've linked him to this mem bucket.
Okay.
We've kind of said mem bucket, just so you know, you currently hold the value of this variable name.
Okay.
Because somebody might come around and ask you about that soon. Make sense? This is like our way of flagging a mem bucket as actually holding the value associated with a variable, so our compiler will work. Okay, so this guy gets the value given a var name. And we have the set of value given address, and we have a set var name given address. So now we have the way of getting a variable name associated with an address, and we have a way of getting a value associated with an address, and then we have a way of asking for the value given a variable name. So we have those 3 abilities now that we've added to data memory for dealing with this stuff. Make sense?
Yep.
All right, so now if we go back into here, let's see, do we need to do anything with our int? So this guy, so let's now revisit this guy up here in terms of our data memory. All right, so this is the point in time. So inside here, when I first declare a variable, this is when I would be associating a mem bucket with a variable name. Make sense? At this point, I know the variable name and I know the location. I don't know the value yet, but I know the variable name and I know the location. So we're going to do a couple of things here. Here is my variable name. I already have that stored. Now I am going to want to store this address for new memory. That's, I need that location, right? So I'm going to go ahead and say int location is equal to this dot data memory dot get address for new memory, and that's going to give me a location. And then I'll just go ahead and concatenate on the location there. Okay, but now I have those 2 pieces of information. So what I've created here is a string that will output, the mips assembly for all this. But I need to do one last piece. My dying wish here is to make sure that data memory, well, actually, I'll do a couple of things here. I want to make sure that data memory knows that this value is associated, or this variable name is associated with that location.
Yeah, you have to add the ladder.
Yeah. So this guy, I have the data memory. This dot, the data memory dot set var name given address. My location is called location. My var name is called var name. That makes sense? All right. So now I've updated my data memory with that location and that var name, which will be the result of creating this variable name. Now, if we go back and look at it at this level, what have I done? I've staged a memory address for holding a variable name. Now, notice that these things kind of come in 1-2 punches, but the question would be is, so the second line, at this point, we're always imagining these two things happening right after each other.
Yeah, in consequence.
Right? Define a variable, then set that variable to equal to something. So if we always assume they're right next to each other, releasing registers isn't overly important. Right? It's like, okay, well, I put your memory address into T0. I have it. I have the memory address. So if you want to give that guy a value, then I'll go ahead and I will, put the value in another register. No harm, no foul. And then I'll go ahead and store that value associated with that memory address. But we have no guarantee in reality of having your variable definition and your value right next to each other. They could be hundreds of lines apart. And in between those two lines, hopefully you didn't use the variable before you gave it a value, but in between those two lines, you probably use quite a few registers. So it wouldn't make tons of sense for us to hold up the process by having this register sit here and just being held down with a memory address when we don't actually use it yet. All right, so we're going to upgrade this guy a little bit by giving us accurate assembly code by not necessarily presuming that register is the register. Okay? So what we're going to do is as soon as we're done using a register, we're going to release the register. All right. So we need to teach our registers how to release themselves. So we're going to do something pretty similar on what we did before. We'll go ahead and we're giving ourselves a function because otherwise we might have, the argument might be is that this is pretty simple code. Duplicating it in two places isn't the end of the world. But good programming practice might say private void, what did I call it in the other one? Just so I'm consistent. Init, I called it a init bucket. We'll call this guy a init register.
That's a nice one.
Init register. And when we're setting a register, it's going to have a name, but then all this stuff is the initialization thing. So we'll say this dot init register. And then we're going to go, do we also call it release in membucket?
Yeah, we call it release.
Yep. So we'll say public void release, and this will also call a init register. So when we release a register, we're not undoing its name. He's still called T0. We're just saying somebody else is now allowed to use this dude because I'm done with them for the moment. Okay. If it happens to be the very next line of code, then we technically were a little bit inefficient because what we're actually going to do is we're going to have to release the register, pretend like we don't have the value, and then immediately use the register again.
And load it.
Yeah. We could cheat. We could do this actually. We could ask the very next statement and say, get the register given that thing, and find out if that register, we can ask, is there a register that already has that variable name associated with it?
But does that in the register? I think it sounds like fake.
Well, this is our behind the scene code. Yeah.
But I guess it's probably should be say, because there is optimization part, like a compile. So part of the optimization can omit this actual release.
Well, right, and that's what we're going to do. We're going to ask the question. So we don't have to. We can always just assume that, look, whether I have the value already loaded in the register or not, I'm just going to load it again. Because that's what I do, and I don't. Why check when I can just do it? In fact, we're going to actually write that write it that way, because what we're going to do in our current thing, now that we have a way to release it, is we're going to make the assumption, since I said in the homework we didn't have to do efficient code, it just has to be accurate code. We can go ahead and inside of our MIPS compiler here, once I've gotten to this line here, we can say that the var name has been associated with a mem location. That's done. It's written to data memory. So any register stuff that I had in here is now free. So what I'm going to do is I'm going to say, let's see, this is register name, right? So I'm going to say string reg name is equal to, I'm going to steal the name of this register.
At this moment, the get next variable register name is not necessary.
Yeah, we don't actually need to pass it a var name, but we're going to leave it for now.
Yeah.
All right, so I'm going to go ahead and store the name of the register that I just used, because after I've stored it, and after I've outputted the assembly code here, and after I've done all this stuff and got my location and written all the assembly, at this point here, this line actually associates a real memory location with that variable name. At that point, I am done with all my registers. So this reg name that I have here is actually no longer needed, and I can give it back so that somebody else can use it in a second. So we're going to go back into our, what do we call it? Register collection. So a register collection, we have a way of getting a register name given a var name. We can get another register. So what we want to do is we want to have the ability of resetting a register given its name. So we're going to say public void reset register. What is it? Release? Is that the word we used? Release register given name. So we'll pass that guy a register name. We'll spin through all of our registers. So we'll say for register R in this dot the registers. If R dot get name dot equals reg name, then I'll say R dot release. And then actually we'll just say return. So that's what this guy will do. Return makes a method immediately end. So this is gonna, I'm saying I want to release the register named this. So I'm gonna go through all my registers. I'll ask this guy, is your name the register I'm looking for? If you are, release yourself. What does release do for our register? Release calls our init register, which zeroes out the value, marks it as not being in use, and clears any variable name associated with it. And then we return. We've already done our job. We've reset the register. This guy's now complete. So then in our MIPS compiler, we can say we can now release reg name. So we'll say this dot the register collection dot release register given name reg name. I use the register for a moment to give myself access to the correct things for my assembly, and got my output for my output string, got my memory, associated real memory with that variable name so I can look it up later, and then gave the registers back so that the next thing that happens in your code has access to that register. If it commonly is the very next thing, if we say I, int I, and then we say I equals 7, we technically wasted a little time here by releasing the register, but we'll just reload the register and move on with life. It's not the end of the world. Okay, so At this point, I think we've roughly optimized what's happening in here.
Yep.
That makes some sense. All right, so our next step is going to be to go in and optimize what's happening in here. So let's take 5 minutes. Sound good? So we'll take a 5-minute break. We'll come back at 7:19. 7:19.